Hello there. Today we're going to look at ExT5 towards extreme multitask scaling for transfer learning by researchers of Google Research and DeepMind. This paper introduces two new things. The first thing is this ExMix, which stands for extreme mixture. This is a dataset. It's actually a collection. They say a massive collection of 107 supervised NLP tasks across diverse domains and task families. So this is a big collection of tasks, and using that collection, they train this new model, ExT5, which, as you can guess, is a T5 model trained on this ExMix dataset, or pre-trained on this ExT5 dataset. And by doing that, they can show that this model, once you fine-tune it on the downstream tasks, achieves much better performance than if you were to pre-train with less tasks or just something like language modeling. In fact, the final model they come up with is a mix of the language model, self-supervised pre-training task, and training on these 107 supervised tasks all at the same time. And that seems to be a strong model. It outperforms, they say, strong T5 baselines on superglue and a bunch of other tasks. Some tasks which are inside of the training set. So some tasks are going to be part of those 107 tasks, but some aren't. And even on those tasks, the model drastically improves over other models, such as T5. So we're going to look at what the data set here, how it is constructed, and I like the way they approach this right here and the kind of ablation experiments they do to show that really the scale of, or the amount of tasks and the diversity of tasks is what really makes the difference right here. At least they give some good evidence for that hypothesis. It could still be that the selection is important, but you'll see. Yeah, that's the overview. Let's dive into it. So what is T5? T5 is this model, this idea that we can solve any NLP task with essentially the same model. So a T5 model is a language model. The language model gets a few tokens as an input and is asked to complete the sequence or to continue the sequence. This is a standard language model, right? If you have a sentence starting here, you can ask the model to complete the sentence. However, there are other tasks than language modeling in NLP. There is, for example, question answering. Now, in question answering, you want to come up with an answer. Maybe the answer is part of the document. So this is your document, right? And you want to come up with an answer to a question that is answered in the document, and you would point out, here is the answer, right? That is what you would do if you were to do something like BERT, like a BERT model. You would put on top here, you would feed all the sequence in, and then the BERT model would output for these tokens, this is the answer. Not with T5. With T5, what you would do is you would ask the model in a language modeling way to continue here and give you the answer, essentially give you these tokens. So everything is formulated as a language modeling task, and this is done by using clever prompting. So here you can see a list of these tasks. This is the same for T5 and ExT5. The difference between them is that ExT5 is pre-trained on a much larger set of such tasks. So, for example, if the task is question answering, the input is this right here. As you can see, it says question colon, right? And this here, that's kind of the pre-prompt, this question colon. That's sort of prompting the model to now do question answering. What does the sun represent on the Uruguay flag? And the answer is the May Revolution of 1810. Here is some other, I guess this is what dialogue modeling. Person 1. So, true story, I once swam with Monterey and it was awesome. Person 2, colon, right? You see this format, this person 1 colon, person 2 colon. This is how they represent dialogue modeling. So you don't have to build a separate model for each task. You simply have to find a way to formulate the task in a language modeling way, such that you can indicate to the model what kind of task it is by using a prompt structure, and then the model will sort of recognize what this is. You may have seen, right? You may have seen this in GPT-3. Now the difference is, in GPT-3 you can do prompts like this, and you probably will get an answer here that fits to person 2. The difference is GPT-3 during training time has only done language modeling, nothing else but language modeling. And then it simply has picked up these patterns as it went along, sort of learning from what was scraped from the internet. However, T5 here is explicitly trained on these tasks. So prompts like these will actually be part of the training set. Now, it doesn't mean that, so you can do then two things once you train such a model. You can evaluate it on tasks that have been in the training set, be that on the evaluation sets of the respective tasks, but they would still be considered sort of in distribution tasks. So you've explicitly trained the model for these tasks. Or you can test it on out of distribution tasks, which is, here would be a task, like a different task, but you haven't trained on that task, but you use the trained model to evaluate on it. This comes much closer to something like GPT-3, right? You have done supervised pre-training here, but the supervision was on a way different task than what you evaluate. So we're going to see these two different things. So that's the idea of T5. They pair this here with language modeling. So there is this one pre-training task right here that, as you can see, masks out a bunch of parts of a piece of text, and then the model is asked to reconstruct it. Again, it's asked to reconstruct it in a language modeling way. So this whole thing will be your prompt with these special mask tokens, and then this whole piece of text right here would be the output, and you would train the model to produce that output, right? Something like GPT-3 is probably not going to produce the output in a structured way where it says, well, mask 0 and then mask 1 and so on. So those are the mixture. It's a 107 supervised tasks. And then this here, I think, comes from Common Crawl from C4. You just do self-supervised training on top of that. And you mix all of that together during training, and then you have apparently a super powerful model that if you take it and you fine-tune it on a downstream task, it is going to perform quite well. That's essentially the whole model. It is not conceptually different from T5. It's simply this fact that we now have the 107 tasks. So they have a split up of what the 107 tasks are, but mostly they fall into kind of different categories. Here they have these task families. There's summarization, dialogue modeling, natural language inference, so classification, semantic parsing, common sense, closed book question answering, and reading comprehension. So this is quite a different selection of tasks. You can see that there's wide, like dialogue modeling might require some real world sort of knowledge to be in there. You can see Wizards of Wikipedia is in that data set, but also there is something like semantic parsing. So you've already seen FuncQL up here. So this is the input, parse to FuncQL. Give me a list of airlines in Pittsburgh. And it will actually transfer or translate this prompt, this natural language input, to a FuncQL or Funkel, I don't even know how to say that, output. You can see the tasks are quite diverse, but in all of them you have to sort of do something with the language, right? Beyond just language modeling. Right, so they now do a bunch of different experiments. And the first experiment is with respect to these task families. They wonder, does it help or kind of hurt if we include a dialogue task for another dialogue task, if we include an NLI task for a dialogue task, and so on. They want to understand, how do these tasks sort of fit together? Do they help each other? Do they hurt each other? Or, what's going on? And for that, so in this here, they have like some intra-family correlations, and turns out most tasks in the same family actually help each other, though not all, which is weird. But the families are, of course, something arbitrary that the author simply laid on top of these 107 different tasks, right? So it's not necessarily the case that all the within family tasks are necessarily so similar to each other. Though the authors say that there are some of the 107 that fit no category. So the categories here are simply for evaluating some measures of how the tasks help each other. So now what they do is if I understand this correctly, they take a pre-trained model, presumably a T5 model, if I understand this correctly. So they take it, maybe not a T5. I don't actually have this present in my mind. However, they take some model that has been pre-trained on something, maybe not pre-trained at all, and they fine-tune it on two tasks at the same time. So rather than fine-tuning it on one task, they fine-tune it on two tasks, or respectively here, rather than fine-tuning it on one task family, such as the NLI family, they fine-tune it on two together. Okay, so here you can, this cell right here is what if I fine-tune on NLI tasks and on CLS tasks together, okay? And I fine-tune on them together, and then I evaluate on the column. So row I, column J, I evaluate the performance on family J. So I fine-tune on classification and NLI together, and then I look at the performance on NLI, on the test sets of these tasks, right? And my question is that more or less than if I were to just fine-tune on NLI, which is this diagonal entry right here? I fine-tune on NLI and NLI, given the same compute budget, select one of these two numbers. One is sort of the data equivalent to both tasks, and one is the compute equivalent. You can choose, but given that this cell is green right here, I think the authors have chosen the top number to be sort of the more representative one. In this case, you see that co-training classification tasks and NLI tasks benefits NLI task evaluation compared to just fine-tuning on NLI tasks. Okay, that's how you read these numbers, or maybe I'm wrong, but that's how I think you read these numbers. So on the other hand, you look, for example, right here, you have this CMNS. I don't actually remember what that family, the name is. It gets a performance of 68.24 if it's just trained by itself, if it's fine-tuned by itself. If you add the CBQA family, it gains in performance. Wait a minute, it is green. Column family J, column J. This is a column, right? Could this be actually row? No, this is smaller than this. Why is this green? Why is it green? I'm confused. Maybe they have to compare with the average right here. I'm confused by this table. I thought it meant if you co-train on the two, actually it gets better. However, the 66 is clearly smaller than the 68. So maybe they consider the row, not the column. I don't know. No, they do consider the column, because then in the text they say, look, for example, adding an NLI task, you can see in the row, this is whatever happens to another task if you add the NLI tasks. This is very often beneficial, right? You can see right here, it's very often a good thing to add the NLI task. For example, but then on the other hand, the summarization task, it's often very negative if you add a summarization task. So it is not, the result from this experiment, at least they say, is that it is not clear whether or not adding more or fine-tuning on multiple tasks together helps or hurts ultimately, right? So that is already very special recognition. This is not yet pre-training, but it is something about training multiple tasks together. It doesn't always seem to help for the end result. Okay, so I think I figured it out. Yeah, I think they do in fact compare to the lower row right here. And this row is the average without regarding the diagonal. So this is on average, how does a given task fare when you add other tasks or other task families? And then they evaluate whether there is a significant deviation, to the top or to the bottom. With the red and green numbers. So mystery solved, yay. I think the lesson from this is that it is not entirely clear that co-training helps here. And now what they do is they go and they say, okay, can we figure out, we have 107 tasks, and we set ourselves one goal, which is superglue, which is one of the common benchmarks in NLP. I think it itself consists of, I believe, 11 subtasks or something like this, and is most common reported in these NLP papers that do multiple tasks. So superglue is the benchmark. Can we find a subset of these 107 tasks that when we pre-train on these tasks and then fine-tune on superglue, it's going to be very, very good on superglue, right? Because given from this table, it's not entirely clear that we should include all of the tasks because they sometimes might hurt each other. So now we're going to try to say, can we find a subset that is just really good for the superglue downstream task? And what the authors do is they do different things. So vanilla, I believe, is you pre-train on 0 tasks. You just train on superglue. Okay, cool. And then this random 55 is simply 55 random tasks. Now, why 55? I don't know. It might be because it's kind of half of what they have, or because it very narrowly beats whatever they have here. The best effort. The best effort is the author saying, okay, let's look at superglue. I'm not exactly even sure what. So let's look at superglue, and let's look at all of the sort of helpful families right here. They say specifically we include NLI, common sense, classification, and closed book QA tasks from the ExMix to form a mixture of 48 tasks to include in a multitask pre-training setup. So you can see those are the tasks right here. If I see this correctly, these 4 tasks that all have the green numbers right here. So on average, these task families help other tasks. And as you can see, this is 48 tasks that were selected after extensive evaluation. And simply by picking 55 random tasks, you're already better in the downstream performance on superglue. Keep in mind, this table here is co-fine-tuning or co-training on 2 tasks and then evaluating on one of them, which is different than pre-training on a task and then fine-tuning and evaluating on another one. But still, it is sort of an effort by the authors to say, what could we do right here? And yeah, as you can see, the final result obviously is that if you use all 107 tasks, you get way better results. So it seems to be, this is a good indication that it is really about the scale and diversity, and might not matter too much that you have this huge task overlap. Although it could very well be that neither the best effort case nor the random sampling right here have really hit sort of the tasks to include, and there might actually be a subset that is even better, but it's kind of unlikely. They've done a different thing where they compare pre-training versus pre-fine-tuning. So pre-training is I train on the supervised tasks and on language modeling all at the same time, and then I fine-tune once on my target task. And pre-fine-tuning is I first do sort of pre-training. In fact, they start with a standard T5 based checkpoint, and then after that concluded, they what they call pre-fine-tune. So essentially it is another step of pre-training, but starting from a checkpoint. They pre-fine-tune with this ExMix dataset. And after this phase, we fine-tune on superglue. So to compare, the comparison is simply that you have like a pre-training, and then you have a pre-fine-tuning, which is where this ExMix dataset goes in. And then you have a fine-tuning and an eval on the same dataset. And they compare the setting where you do the 3 in stages right here, compared to when you do these 2 things at the same time, and then you fine-tune and evaluate. Okay. The bottom row is sort of the baseline, and the top row is what they actually suggest. What they suggest is that, hey, we should just do all the pre-training at the same time on the supervised tasks, on the self-supervised tasks, and so on. So here you can see, if you simply take vanilla model, fine-tune it on superglue, you get a 76.1. I'm going to guess that's the T5 base checkpoint right here. Then if you pre-fine-tune that checkpoint on ExMix, you do get 78.1 on superglue, which is a considerable increase, right? However, if you simply do the same, but include that ExMix dataset into the pre-training, you do get an even bigger boost. So how do we make sense of that? That is a good question. I'm not entirely sure, but maybe a hypothesis. So I've in the comments, but one hypothesis here is that I have is that a supervised NLP dataset, if you look at these tasks right here, what does it really mean to be a supervised NLP dataset? What it means is that by determining a label to a prompt, you sort of, as a labeler, bring in additional knowledge that is not just in the text, right? So, in order for you to parse this kind of funcal query, you have to know a bunch of things. So give me a list of airlines in Pittsburgh. You can see right here, okay, Pittsburgh, there is like city name. Okay, so you need to recognize this is a city. This is already information that you kind of bring into the model that just goes beyond language modeling, right? Services, so the recognition that an airline is servicing a city. That is, again, it's kind of real world knowledge. So I think that, if you compare having these tasks here versus having just self-supervised pre-training, it is a bit deceitful that you say, well, we train on the same amount of tokens, or we train for the same amount of steps, because I think the labeled examples are much more information dense, because they sort of bring in knowledge that is not in the tokens themselves, but kind of in just like in the in the positioning of the label with prompt, you bring in additional knowledge that, it's not the same as simply a piece of text with that many tokens. That is one of the observations that I, for myself, could make right here, why this is quite helpful. So it conveys world knowledge, or it conveys grammar knowledge or whatnot to the model by means of these labeled datasets. The second thing is that I do think we have a lot of evidence that especially the beginning of neural network training are quite important. So in a neural network, you never quite get rid of your pre-training. So I think that explains this right here. We know that if you pre-train, it doesn't matter how many steps of fine-tuning and fine-tuning and fine-tuning you have, the pre-training, especially the one at the very beginning, will always be somewhat represented in that model. It will always influence a model quite a bit, how you exactly pre-train or on what. It's almost like you have kind of like endless possibilities to go as a model from your initialization, right? And then once you've picked one, once you've picked one of these directions, all you can really do is kind of wiggle your way into better local optima, but they're all essentially in the same conceptual area, like in the same direction right here. And if you were to start with a different data set, you might choose a very different direction at the beginning, one much more amenable to the kind of natural language inference prompts that you're going to do. That is like a hypothesis that could be, right? And that would kind of explain why pre-fine-tuning works less well than simply pre-training from the get-go on the multiple tasks. So what do we learn? Initialization or early stages of training might be quite important, especially for like generative models like these. They go further and they ask themselves, since I've shown you that they have, in addition to all the supervised tasks, they have this top row right here, which is this self-supervised tasks that you're used to from language model. It's formulated a bit differently with the prompt input and the prompt output, but essentially this is masked language modeling like you'd encounter in like BERT, in the form of autoregressive language modeling as you would encounter it in a GPT model. So the question is, of course, you have 2 data sets. So even if you somehow manage of these 107 data sets to get roughly like equal data for each one, how should you mix the self-supervised objective with the supervised objective? And the answer is you should somewhat mix them, and how much, that's detailed in the plot here. So you can see right here, R is the ratio of self-supervised to supervised pre-training data, and then the y-axis is the performance when fine-tuned on superglue. Now, if you go to the right, you can see that the blue line approaches the dashed line, and the dashed line is simply the performance without any supervised data at all. So if you simply pre-train on the masked language modeling and then you fine-tune on superglue, it makes sense. As R goes to infinity, the proportion of supervised data approaches 0. So that blue line must meet the dashed line. However, it's pretty interesting what happens at the beginning. Note that if R is 0, the performance is terrible. That means if you only have like supervised tasks, that is crap. That is just not good at all. And I think this might even be like this. I think this is super important recognition, for all the, wow, you need a lot of tasks and so on. If you don't have your language model pre-training, if you don't have your self-supervised pre-training, even if you have the same amount of data points, it is going to be crap, right? So there is something for having these self-supervised tasks right here and having the model actually learn these like grammar and continuing just bland pieces of text that are not geared towards some specific task. Because, if you then have to pick up on new tasks, it kind of helps you that you've just been around language, it seems. And this is also a hypothesis, is that these supervised datasets, by means of all being on the same task, right? Every one of these 107 datasets contains data points that is like structured exactly the same. The amount of world knowledge in there is quite big, yet the amount of language knowledge in there is quite small, right? All the Funkel dataset prompts are gonna look. Not only are they all gonna start with like parse to Funkel : but they're gonna kind of look the same. Like they're gonna be like the sentences are gonna be very much the same. The answers are gonna be, well, they're not even text, but also they're all like very much the same. You're not gonna get random text in such a query. You're gonna get text, for the entities it knows and for the kinds of facts that it wants to express. So the supervised datasets, while being good in having labels, they're quite bad at actually expressing language, which is interesting, right? Because it is something that is especially pronounced in language, I feel. Because if we, for example, look at images, I guess it might hurt too if we had like ImageNet, but so if we had like huge ImageNet, maybe it still hurt because it's only like the 1,000 classes, and images tend, like ImageNet images that are made for classification tend to like display one particular object in the middle. Yeah, I don't know. But in language, certainly, like NLP tasks, they have super limited language. So it's important. Towards here, we approach, obviously, the performance without supervised data. If we don't have any self-supervised data, it just does not work, or it just works very poorly. However, there is an interesting regime right here. As you can see, as soon as we hit 1, which means equal amount of self-supervised and supervised data, our performance improves over just using self-supervised data. And then if the ratio is 2, that seems to work quite well. As you can see right here, that is almost 80. That's quite a big jump in superglue performance. However, as we know, if R grows, this must come down again, and it comes down pretty quickly. Already at 4, it seems to be almost back to where it started and then kind of wobbling around, or so it seems. These experiments are big, so you can't exactly fault the authors for not evaluating many times and giving error bars, though here in this case it would have been quite nice. So you can see the window is quite narrow, and that is a little bit of a disappointment by me, or a bit of a criticism here, is that yes, it's good that you can get something if you have this many pre-training tasks and so on, but in a real world scenario, right? I don't know how much I need of that, right? I could go with a good guess and say, well, probably other data sets have similar behaviors as superglue, but who knows? And generally, if windows are so small for hyperparameters, it's a bit of a risk. And if in practice I always have to do giant experiments to evaluate whether that hyperparameter setting is still appropriate, and it's not really a gain, because it doesn't save me anything, because I always have to do this evaluation. But maybe this turns out to be fairly robust, this number 2. Who knows? In their experiments, at least it did. Then they go on and they ask, okay, so we got 107 tasks. If we simply pick random subsets of these tasks, how does that impact performance? As you can see, there is trend-ish thing sort of upwards. There is a bit of a downwards here, but nobody knows, because as you can see, here we do kind of have error bars, and they're kind of big, the standard deviations. What you can also see is that for larger batch sizes, the trend seems to be kind of more consistent and better. We've known for a while that larger batch sizes help these things, but I guess especially if you have so many different tasks together, having a big batch size means that it's much more probable that you have sort of balanced data, that you don't end up with a batch with only data from one particular task, which kind of wanks all the other weights out of whack. Or if you have like 2 or 3 batches, one after another of these, it can be quite detrimental. So that is maybe one, but yeah, that like the standard deviations are quite big, as you can see, but clearly the higher batch size is better, even if they have like the same compute budget, right? So it's not like the higher batch size experiment like saw more data. At least I don't think so, or had more compute. And the last thing is they compare during training. So they ask themselves, which is this really sample efficient? And the answer is, compared to like a T5 model, yes, it's quite sample efficient. As you can see right here, comparing these two models, you can see that even after the same amount of compute, after the same amount of steps, the ExT5 model is quite a bit higher than the T5 model. So it's not just at the end, it's in fact during all of training. So you could potentially stop earlier and get like the same performance as the T5 model would get much later in the training. So for example, this point here is already reached here way earlier. Of course, the longer you go out, the more extreme this effect gets. And that's basically it for the ablation experiments. This is the part of the paper that I quite liked, because it's kind of investigative and it sort of justifies their choices. And the choices are pretty simple, right? It's just like throw everything in there and do everything at the same time. But instead of just doing it and then evaluating, which they do down here, obviously they're kind of better at most things. In distribution tasks, out of distribution tasks, yada yada yada. Like they're better. Like, trust me. Though it is interesting to see that very often they're not that much better. Like they're kind of like, all right, T5 gets like 29.01 and you get like 29.49. Like, who knows how big of a difference this is? It is. I guess for machine translation, that is a difference. Still, it's not that much, honestly. On other tasks, you can see right here, the T5 gets, what is this, 55, and this is 63. This is quite a big difference. I think I saw other tables where the differences were even more drastically. So it seems to really depend on the task as well, whether or not this can get you a gain or not. Yeah, so I quite liked this investigation into, are we doing the right thing, even though what they want to do is the most simple thing, is just like throw everything together into one giant model and add some self-supervised as well at the same time. But yeah, it is interesting to see. And if you want to learn more and dig into their exact results right here, this is all available. In the appendix, there is a split of exactly how the 107 tasks are, if I understand correctly. Here you can see the different data sets used to construct ExMix, implementation details, and so on. It is quite thorough. Yeah. So that was it for ExT5. In summary, this is a T5 model that has been supercharged by pre-training it on a combined language modeling objective and supervised objective that is a mixture of 107 different NLP tasks, all at the same time in a ratio of 2 parts of self-supervised and 1 part of supervised data. And that turns out to perform extremely well if you fine tune it on a downstream task. And in fact, it's not really easily possible to outdo that recipe by doing something smarter out of the box. So by selecting a good subset of tasks, or by or what was my point right here? Or by somehow staggering the things, like doing it like first the pre-training and then the pre-fine-tuning and so on. It's not easy to beat it. That was my point, my 2 cents on this paper. If you enjoyed it, leave a like. If you didn't enjoy it, I guess you can leave a dislike, but you know, what's it gonna do, honestly? YouTube, I still see it, right? I still see how many dislikes I got, but if you disliked the video, tell me in a comment what you disliked. All right, I'll see you next time. Bye-bye.